this is section number 3 of this thermodynamics class. So if you have any confusion from the last section, you will understand what is thermodynamic equilibrium. You will definitely get a question what is thermodynamic equilibrium in the book. It may be in different way, but you will get a question. What do you understand by thermodynamic equilibrium in better point of view? You can give this example which I explained in the class, right? Okay, fine. So we in the last maybe we were discussing about that all the natural occurring processes are basically irreversible in nature, right? Basically, they are spontaneous because we have discussed three terms now. One is driving force, one is spontaneity, a spontaneous process, one is feasibility. Right? So suppose since we are metallurgy people, so we basically extract metals, we basically refine the metals, which basically involves chemical reactions. You need to have reactants, you need to get products. Basically reactants are overall minerals, but products are metals or alloys or impure metals. Right? Because first stage is production, next stage is refining. So you will get impure metal, then you can refine it. Right? And most of the process, if you see, they are pyrometallurgical process because they involve high temperature or heat energy. Right? As I told, in the steel making process is pyrometallurgical process. Iron extraction is also pyrometallurgical process. That's because they involve high temperature or heat energy. Right? And they are also carried out in a reactor. Right? If I will take that is a reactor, inside the reactor, these processes are carried out. And technically we call it as a furnace. We metallurgical call it as a furnace. F-U-R-N-S-E. Furnace. Furnace means which can provide very high temperature. And inside that you can extract the metals. Okay. So here there is concept of thermodynamic system, thermodynamic surrounding or universe. See, the entire thing is universe itself, right? We are in the universe. Right? Entire thing is universe only. We don't know what is the end of the universe, what is the boundary. We don't know that till now. So, if you consider any portion of the universe, or the portion of the universe which is taken into consideration, that part is called thermodynamic system. For example, this classroom itself, this entire classroom have a boundary, fixed boundary, right? So this entire classroom is right now you can say this is a thermodynamic system. Because we are also there, we are releasing energy, we are also consuming energy, right? Heat is flowing in and outside, air is also going in and outside, right? Mass is also moving, right? Heat is also moving, of course, no? Right? We are, myself is also a thermodynamic system itself, right? Because I am consuming food and it is generating energy, I can able to run, walk, or teach or whatever, right? Energy is moving, right? Heat is moving, of course. You people know thermodynamic systems, right? Basically, it is open thermodynamics. We are open thermodynamic system. I will tell you that. So thermodynamic system exactly means any portion of the universe, if you take for consideration, and that portion is called thermodynamic system. It can be anything. I am also thermodynamic system, that means I have a boundary, right? Apart from the thermodynamic system, everything is surrounding. So this classroom is system now. So surrounding will be that classroom, the corridors, those plants, air and all, everything. Right? So in simple word I can say universe means system, thermodynamic system plus surrounding. This mobile itself is a thermodynamic system, I can say. So apart from this mobile, everything is surrounding for that. She, me, you, all are surrounding for that. Is it okay? So this VSS we have a particular boundary. So entire VSS we can consider as a thermodynamic system. Apart from it, the roads, the air and everything is surrounding. Okay? So I can say system plus surrounding is nothing but the universe. Okay? So that means we can have open systems, we can have closed systems, we can have isolated systems. Right? These are the three thermodynamic systems we can have. Right? So open system is exactly what two things can be transferred. One is mass or the matter you can say, and one is the energy. Okay. These two things can be transferred. So as I told, I am a thermodynamic system, so I am eating some food, for example, right? So some mass is getting transferred from outside to me, or from the surrounding to me, right? Then that will be digested and it will produce some energy. That energy will, I can do some work later, whatever, right? So that is mass is getting transferred into me, and everybody eats food, okay, fine, right? And the unwanted substance get removed, of course, from our body later, right? So mass is going out from our body also, right? And the point is, we are also inhaling, right? We are also inhaling the oxygen. Again, some mass is going inside it, right? And from the atmosphere, some heat energy is also coming into my body, and I am also releasing some heat energy. The moment I am running, for example, right? So I am getting sweat. Why I am getting? Because the temperature is high in my body, and it is getting dissipated to the atmosphere at the time. Okay. Fine. So heat is also going out. Heat is also. So in the summer you feel heat more hot, right? Why? Because the temperature is high in the surrounding. It is moving into your body. That's why you are feeling hot. Okay. During winter, what is happening? You are feeling cold. Why? Because the atmosphere, the surrounding is colder, but your body is hotter. So again, your heat is getting dissipated to the surrounding. So heat is moving into your body and going out of your body. Mass is also moving into your body and going out of the body. That means there is an exchange of mass and there is an exchange of heat between system and surrounding. So that system is called open system. Is it okay? Similarly, closed system you can understand. Closed system is that system where only energy can be transferred between surrounding and the system, but mass will not move. For example, I will take a okay, fine. Suppose you are doing some work and your mom called you that take this cup of tea, fine. So you forget, you put it on the table, you forget it. So what will happen after some time? It will become cold because it lost the heat, and maybe some water vapor will also get evaporated, of course, because it is at high temperature. So some water vapor will also. So it is an open system. Fine. A cup of tea, hot cup of tea is an open system because some moisture will go out and heat will also get lost to the surrounding. But if you close it, right? If you close it simply, or you put it in a bottle, for example, so no mass loss will be there. Whatever the mass will be there inside only, but heat will get lost with time. It will become colder, right? So that is actually closed. Is it okay? So where only there is exchange of heat, but there is no exchange of mass, that is a closed system, right? So last one is isolated system, and I know you people know what is isolated system. Can you give an example? Thermoflask, yeah, you know that. But do you think that thermoflask is exactly an isolated system? 100% no. Because after maybe 10 hours or maybe 12 hours, it will lose the heat. The temperature goes down. It is not ideally isolated. There is no system which is isolated actually. It is very difficult. Always difficult. It may take time to release the heat. You can produce a closed system, but you cannot produce a very ideal isolated system. If isolated system means there will be no exchange of mass, there will be no exchange of heat between the system and surrounding. But thermoflask, after 10 hours or 12 hours, it becomes cooler. Of course, it will lose the heat. It can be an ideal closed system. But you can give an example. Thermoflask is an example of isolated system, but it is not 100% isolated. Okay, up to this it is clear. Then yeah. So some people have confusion in this irreversibility. Okay, let me take one another example of open system. Whatever reactors we are working to produce metals, right? Those are also open systems. Those are also open systems because continuously we are feeding the ore into the reactor because mass is getting transferred, right? And you are supplying some heat energy, external heat energy. Heat is also moving into the system, and some heat is also generated inside the body, inside the reactor, and it is also moving out through the products. So products are moving out, mass is moving out, right? Metals and slag will move out, but you are feeding ore, right? And some those metals and slag are in also molten state, so they will carry some sensible heat. Heat is also moving out, and some heat energy will also dissipate, lost into the atmosphere. So all the reactors basically we are working on are open systems. From metallurgical point of view, if somebody will ask, can you give an example of open system related to metallurgy? You can say all the reactors which we use to produce metals are open systems. So mass is moving, energy is moving, also energy is coming out, and mass is also coming out. Yes, example. Best example is blast furnace. We can discuss something about that. Blast furnace. It produces iron, actually, pig iron. Have you ever heard about this term, pig iron? Pig iron, you know? Why it is called pig iron? Any idea? Most of the iron we produce is pig iron. Because it resembles to the litter of pig. It resembles to the litter of pig. The color of the iron looks like litter of pig. Litter of pig, you understand that means, yeah. The waste, anyways. So see, this part is very, very important. You may get a question from this. In the mid-sem, irreversible and reversible process. So, what is exactly, let us discuss what is reversible process first. If you remember, I have given an example of a natural process which is a spontaneous process. For example, melting of an ice. You do not have to do anything. You keep the ice cube, it will automatically melt or something. We are not providing any external energy. It is a spontaneous process, right? Melting of ice is an example of spontaneous process. It is also irreversible, but somebody asked me, right? So, but if we go to hill station, so why we go to hill station? Because we want to enjoy the atmosphere. It is somewhat cooler, right? Obviously, it is somewhat cooler in, like for example, Kedarnath. Take an example, Kedarnath, right? So Kedarnath remains closed for some 5 to 6 months. You know why? Because the temperature goes down very low and it is filled of snows completely. Very difficult to stay there because temperature goes down very low, right? So that snow again melts. Of course, snow formed, but again melts. So you can say it is a reversible process. Automatically happening. Of course, you can say it is a reversible process that is happening. Snow is forming, that means liquid becomes solid. Again, the snow becomes liquid. So solid to liquid, liquid to solid, and solid to liquid again. So it can be reversible. But the point is, it is not a reversible process. It is actually irreversible. How I can defend it? So most of the process we are seeing in the day-to-day life are irreversible actually. There is no ideal reversible process. All are basically irreversible. Whatever you are doing or something. We are producing a metal, it is also irreversible. Right? So what is exactly the reversible? Reversible process exactly means if a process is happening in infinite number of steps, small infinite number of steps. It is not happening in one step. It is happening maybe in 1,000 million steps, slowly. And it is happening infinitely slow rate also. In infinite number of steps and in very slow rate. Very slow rate. You cannot identify it. It is happening at a very slow rate. Right? That means the change happening. Suppose heat is releasing. Suppose for example take an example of snow and you want to make it into liquid at a very slow rate. You can have to see the change actually, but it is happening. That means heat is moving out of the snow. That's why it will become liquid later. But it is happening at a very slow rate, infinitely slow. The change is negligible, or the change is infinitely small. The changing heat energy I am talking about because it is releasing, right? So that kind of thing is actually reversible. So reversible process exactly means if a process is happening at a very slow rate, infinitely slow rate, and infinite number of stages or steps, right? And each stage is in equilibrium with one another. Suppose let me give an example. Suppose it is happening in 100 number of steps. For example, your snow want to become liquid, solid want to become liquid, and it is happening in 100 number of steps. Just I am giving an approximation. This is not reality. It may happen in million number of steps. Maybe. So step 1 to step 2, they are in equilibrium. Step 2 to step 3, they are in equilibrium. Why? Because this is happening at a very slow rate. Now you cannot identify the change in temperature. 4 and 5 are in equilibrium. Equilibrium, you remember I told you? There will be no gradient of temperature, there will be no gradient of pressure, there will be no gradient of chemical potential. Gradient means difference. But there is some difference, of course, that's why heat is flowing out. No? But it is happening at a slow rate, so infinite number of steps, you cannot identify it. So this line is important. This line is important means a process is reversible means if the process want to come back again into its original state, completely original state, there should not be any footprint on the universe. Again I am saying, suppose snow is there, right? It is having a certain state, temperature, pressure, mass, everything is there. It become liquid now. For example, it become liquid. Again you want to make the liquid to snow, original. But somewhere you lost some amount of mass. Entire liquid may not be snow, maybe, right? Or your temperature or pressure maybe come back to the original state, maybe. But to the surrounding, some changes has permanently made. It made some changes to the surrounding. Some footprint to the universe is there. Anyhow, how I can justify it? Let me give an example. How a snow will melt? Can we just think about? Sun rays are coming, of course. In winter, snow will be there, right? But in summer, it will melt. So sun rays are coming. Sun rays are very intense in the summer. It will heat up the atmosphere. So atmospheric air will get heated up. And why? Because sun rays are having photons. You know that in physics, right? Packets of energy. How sun is producing energy? By nuclear fusion, of course. Two hydrogen atoms is combining and it is releasing lot of energy and become helium and energy, right? So in this way, what is happening exactly? The sun mass is going down with time, of course. Sun is also losing energy permanently. Whatever energy has reached to us, you cannot send back to the sun again. We have consumed that energy, right? And it gets dissipated somewhere, but it cannot go to the sun. So permanently sun has lost some mass, some energy. So something has changed to the surrounding permanently or to the universe. But you can bring back the system. Thermodynamic system is now what? Your ice cube or your snow is the thermodynamic system now. So thermodynamic system can come back to its original state. Again, it becomes solid, snow. But permanent changes happen to the sun. It has lost its energy, lost some mass. It cannot revert back out completely to its original state now. Do you understand my point? So there is some footprint in the universe, some change in the universe. So that is called irreversible process. Reversible process means entire system and surrounding will come back to its original state. Because that's why we are talking about system and surrounding. We should consider the state of system and state of surrounding also. Okay? And ideally it may not be happen like all the liquid will become ice or snow. Maybe some loss will be there into the atmosphere also. Suppose you have taken 100 gram of water. That 100 gram of water become ice. Then again the ice become liquid. So this changes. It may not be 100 gram. It may be some 99, 98. Some loss is here. Some mass loss will be there. So if your entire system and entire surrounding will not come back to its original state, that means it is irreversible process. Okay. Is it fine or not? But reversible process means entire system and surrounding will be again in its original state. But it is not possible actually in the real life. Some loss will be there due to friction, due to heat dissipation. Some loss will be there, some heat loss will be there, some energy loss will be there, some mass loss will be there, anyhow. Either to the system, to the surrounding. Is it fine? Yeah. So you have to remember, the natural occurring processes are actually spontaneous processes in the real situation, because we do not have to give any amount of energy from our side. Right? It will automatically happen. So that those are actually spontaneous. And you can say those are also irreversible. So all the natural occurring processes are spontaneous and they are irreversible. Thermodynamically irreversible. Because you cannot bring like again to its completely original state. Or if it can be bring, then it may affect the surrounding. Surrounding, some footprint will be there. Or to the universe, some footprint will be there. Some change will be there, of course. Is it fine? So okay. So now we discuss about very important point. This is law of thermodynamics. Laws of thermodynamics. So basically we have maybe in details we will not discuss today. And last one is zero. These are the four number of laws of thermodynamics. First law, second law, third law, and zero. ZERO, zero. So this zero law of thermodynamics, some people call it fourth law, but not exactly fourth. Its name is zero. First, second, third, and zero. Okay, anyway. So first law of thermodynamics basically talks about law of conservation of energy. This is in simple term. That means energy can neither be created nor be destroyed, but it can be transferred from one form to another form. Right? It can be transferred from one form. So energy can neither be created nor be destroyed. Right? That means energy in the universe is constant actually, no? Of course. If your system is losing energy, maybe it is taken away by your surrounding. If your surrounding is losing energy, it may be taken away by the system. So entire universe energy is actually constant. Somewhere, but it is flowing. That's why thermodynamics is called flow of heat or flow of energy. Right? Energy in motion or heat in motion. That's why you call it. Somebody has to absorb, somebody has to release. Okay? But let us give some examples in metallurgical point of view. One example I can give is solidification. Solidification of molten metal. Sometimes people call latent heat of fusion, or sometimes people call enthalpy of fusion. So actually we will discuss that in coming lecture. Actually enthalpy and there is a concept, you know, enthalpy. So enthalpy and heat are actually close, very close. But sometimes we call enthalpy, sometimes we call heat. That we will discuss in coming lecture. You should not be confused, because many people get confused. What is enthalpy? We have studied entire thermodynamics, but we do not know what is actually enthalpy. So enthalpy and heat are actually close. If I am saying enthalpy and heat, they are same actually. But there is some condition when we can say heat, when we can say enthalpy. We will discuss that in coming lecture. Right? This is not right time now. Okay, fine. So solidification of molten metal. So there is a subject also in our metallurgy that is called solidification or casting. We can study in detail. Maybe I will also teach you during physical metallurgy. There is a concept called nucleation and growth. We will not discuss that right now. But the point is, suppose you take a piece of aluminium now and you melt it. What is the melting point of aluminium? Any idea? See, for us, you have to remember some density of some metals and melting point of some metals. Sometimes they ask this question during interview. Simple question, but you cannot able to answer that. So it will bring a bad impression. No. Melting point of some important metals like iron, aluminium, copper, which are mostly used. The mostly used metals are iron, copper and aluminium. These are the three most important metals we use always. Melting point of aluminium is 660 degrees centigrade. 660 degrees centigrade, approximately 660, maybe 659 point something, but consider it as 660. So you take the aluminium solid into molten state now. So what is happening? You are melting it first. That means energy has moved from surrounding to the system. Your piece of aluminium is actually now your system. Energy has moved from the surrounding to the system. It becomes molten now. Now it is at 660. So I am talking about solidification. Solidification means the liquid aluminium has to become solid again, right? So when it will happen? When the temperature will go down below the melting point. Of course. So suppose it is at 700 degrees centigrade. Now you bring it to 660. Keep it for some time at 660. Even if it is at 660, you will find that some solid are also forming. But you will find there is no change in the temperature in that condition. Very interesting. But some solids are forming. Why? Because this latent heat of fusion is getting released from the molten aluminium. So when the latent heat of fusion is released from the molten aluminium, some solid crystals will form. But you cannot observe it for some time. But when the temperature go down further, you can observe how temperature is continuously decreasing. But at constant melting point, some solids will form. Because it is an equilibrium condition, you can say. Solid will be there, liquid will be there. It is the equilibrium condition, kind of. So you understood that. So why I am saying this? Because it obeys the first law of thermodynamics. Energy is neither created nor destroyed. So whatever energy you have provided to the aluminium to melt it, that energy again comes out to the surrounding. So it is not lost. It is moved to the surrounding itself only. Right? So we didn't create it. We just transferred it from molten aluminium to the surrounding. Just transfer. Right? Next example I can give you. Okay, this concept will help you to find out at what temperature or how much, like how fast you can do solidification. This will help you, this concept. Solidification can happen at a very fast, slow rate, or it will take time. Second one you can write like heat balance. Yeah, this is very important. Heat balance. Heat balancing the reactor. Find out coke rate or fuel rate. Find out coke rate or fuel rate. So this is again related to your extractive material. See, if I told this quickly, I can draw a diagram. So this is a very quick diagram I am drawing. You know this, as I told, Fe2O3, some flux, and coke, source of carbon, reductant. And if you remember, slag will be here and molten metal will be here. That is here the P guide. And here we are providing hot air. So this is actually diagram of blast furnace, which produces pig iron. Or we can extract iron by using this kind of furnace or reactor. The name is blast furnace. Blast furnace why? Because we are blasting hot air at a very high velocity. The hot air is given to at a very high velocity, so that's why it is called blasting of air, and name is for blast furnace. Anyway, so just see, I told this is the open reactor, if you remember. Continuously you are feeding the over your coke, reductant, and your flux. And finally you are getting molten slag and molten metal. Molten slag is the impurities part, and metal is the metal having some amount of little amount of impurities. So here you can see what I told. We need to balance the heat. Balance, because this kind of process occurs at a very high temperature, around 1500 degrees centigrade or 1550 or 1600, around this temperature. 1500 to maybe 1600 degrees centigrade. I'm not going into details, but just imagine this temperature is required. This temperature should be maintained. But the temperature is different. If you go from here to here, the temperature will be different. If you go from here to here, the temperature will be different. Temperature will be maximum at this region, that is nearly 2000 degrees centigrade. But temperature go down here, temperature also go down in this direction. Fine. So just see, in this reactor, we are providing what? Solids and some amount of external heat. How the external heat is coming? From the hot air. Okay. So this hot air is carrying the heat energy, and this hot air will react with what? Carbon of the core. So carbon will burn now. Combustion will happen. It will release lot of heat energy. So two types of heat is there. One is sensibly present in the hot air, which will start the combustion of the coke. When the coke will burn, it will also release. This is exothermic process. It will release heat. Fine. So these are the two way you can. These are the two sources of heat. One is sensible heat in the hot air, and due to combustion of coke. And during this process, Fe2O3 will react with carbon, or Fe2O3 will react with carbon monoxide, because when carbon will burn, it will release carbon monoxide also. Now there is certain condition. It may form CO2, it may form CO. Right? Two kind of oxides of carbon, basically. Carbon monoxide will form when there will be incomplete combustion. But there is some condition. Carbon monoxide will only form or will stay when the temperature will be very high, above 950 degrees centigrade, and solid carbons are available. These two things you have to always remember. If you are burning anything which is made up of carbon, basically it forms carbon dioxide. But if fresh carbons are available and you are maintaining a temperature above 950, then carbon dioxide will not form. Carbon monoxide will form. Basically. So carbon monoxide formation requires a particular temperature and certain conditions. Okay, and carbon monoxide is which kind of gas? Oxidizing or releasing? Oxidizing gas means it will oxidize the metal. Releasing gas means it will take away the oxygen from the ore. Oxide. Reducing. Yeah, it is releasing gas. Right? So carbon monoxide will react with Fe2O3, will give rise to CO2 plus Fe. You can say. Similarly, carbon is also a reductant, and carbon monoxide is also a reductant here in this reactor. Do you understand all? Carbon monoxide is a gaseous phase, it is a reductant. It will take away the oxygen from the Fe2O3, and carbon also directly reacts with Fe2O3 to produce Fe. You understand my point? So lot of reduction is happening. So some kind of reduction are exothermic, some kind of reduction are endothermic. Exo means it will release heat, endo means it will absorb the heat. So basically inside the blast furnace, the indirect reductions are basically exothermic in nature, but direct reductions are endothermic in nature. Direct reduction means carbon is directly interacting with Fe2O3. That is direct, and they are basically endo in nature. They consume the heat, right? And exothermic reaction means indirect. When carbon monoxide is reacting with, because carbon will form carbon monoxide, then carbon monoxide is reacting with Fe2O3, that is indirect. That means carbon is not directly interacting with Fe2O3. It first forms carbon monoxide, then you understand my point. So that means, and also the interesting point is, sometimes what happens if you feed, flux means if you feed calcium carbonate. So what will happen? So calcium carbonate is a flux. I am not feeding lime directly. This suppose I am not feeding, I am feeding this one. So what will happen? The calcium carbonate will also decompose. That is called calcination. You have studied in school days. Calcination is a process where thermal decomposition will happen. That means CaCO3 will break down into CaO plus CO2. That is highly endothermic. Again. So again it will consume energy. So my point is finally, in this reactor you are producing iron. It is an open thermodynamic system now. Some processes are providing heat energy, some processes are consuming heat energy. Right? So, and you have to produce liquid slag and liquid metal at the end to take it out. You cannot take out solid things from this now. Once it will enter, you cannot take out solid things. You cannot take it out. It is a continuous process. Temperature is very high. You take out only liquids basically, or some gaseous phase. Okay. Since this inside the reactor endothermic reaction is happening, happening, excavation is happening. So if you just imagine, if more number of endothermic process will happen, what will happen? The slag and metal may freeze. It becomes solid, of course. And reduction also requires some temperature. If the temperature will go down because of endothermic processes, reduction may not happen properly. Your furnace will not work properly. So the production of iron, here for example, this example, needs a particular amount of temperature or particular amount of heat energy should be remain inside the blast furnace. So that's why the concept is called heat balance. Heat balance means how much heat is going inside the reactor, how much heat is accumulating inside the reactor, and how much heat is going out of the reactor. Right? So in simple word I can say heat input is equal to heat accumulated in the reactor plus heat dissipated from the reactor. Or in simple word I can say heat input is equal to heat output. This is always true that this first law is saying same. First law is talking about heat will be that the energy can neither be created nor be destroyed, but it can be transferred. So you are transferring heat into this and some heat is also coming out from the reactor. Right? Again I am saying heat balance means you have to maintain a particular amount of heat energy inside the reactor. If you cannot maintain it, what will happen? The molten metal, molten slag may be solidified. You cannot take it out later. You have to break the furnace to take it out. And this blast furnace is maybe some 100 crores. You cannot do that. You cannot do that. So, and it has to run for 15 to 20 years continuously. Continuous benefiting, continuously you are getting better. For 15 years, it should run. Otherwise, there will be loss to the manufacturer, of course. You get my point. So, this need to maintain a heat balance. Whatever heat input is happening, whatever heat is going out of the system, that should maintain a particular amount of heat. So let me, approximately I am saying, suppose you need to maintain some 1000 kilocalorie of energy. That should maintain. It should not go down, it should not go above. If it should be going above, that means maybe you are losing some heat, it is not a good reactor. Or you are consuming a lot of amount of coke. If heat loss is more, that means you are losing the coke. And the point is coke is very expensive. We do not get coke directly from the nature. We never get coke directly from the nature to produce coke by carbonation process. We have studied previously. High temperature carbonation, low temperature carbonation, where coal become coke at high temperature. In absence of air, if you heat the coal, some kind of coal, not all, basically bituminous coal. There is a particular kind of coal that's called bituminous. Because there are different kind of coals, peat, lignite, bituminous, anthracites. So basically, if you heat the bituminous coal at a very high temperature, in absence of air, it becomes coke. And that coke is used. And in India also, we don't have plenty of bituminous coal. We export it from Australia. So there is a charge of, we are exporting, we have to pay money to Australia, of course. And you know tariffs. Everybody knows, right? If country will put more tariffs, you have to pay more amount of rupees, right? And you know that the dollar price is also increasing day by day. You have to pay more amount of rupees, right? Anyway, so my point of view is what? If heat balance will be not proper, coke consumption or fuel consumption will be more. So cost of iron will be also more. So nobody will buy your iron. Of course, nobody will buy it because you have to sell it at a very high cost because production cost is high. So metal cost will be more. So you always try to use less amount of coke. So how you will decide? You have to check the heat balance. How much heat is going in and how much heat is going out. So how much heat is going in, how you will find out? One heat is sensible heat of hot air. Input heat I am talking about now. And the heat is the heat which released due to combustion of carbon. Okay? And the heat is which is coming out during indirect reduction. These are the three heat inputs I can say in the furnace. One is sensible heat of hot air, one is due to combustion of carbon, and one is due to indirect reduction. And what is heat output? Can you tell me? Just use your mind and just tell me. That is the heat input, I can say, overall heat input. Heat output one will be obviously some heat will dissipate automatically. Why? Because there is a temperature gradient. Atmosphere is cooler, but the reactor is hotter. Of course, heat will flow from high temperature zone to low temperature automatically. Because I told you, there should be always an equilibrium. system always want to be in equilibrium, so they will release the heat automatically. Some heat will be dissipated, right? Through this automatically. You don't have to. Some heat will also dissipate from here. Heat loss. That is one heat output, and the heat output will be what? As I told, continuously you are feeding, continuously you are taking off slag and metal, and they are in molten state. Molten state means very high temperature, 1500, 1600 degrees centigrade. Right? So that also carries sensibly this molten slag and molten metal. That is also output heat. Fine. Do you understand my point? And I told, if you are using flux here as a calcium carbonate, calcination will happen. That is endothermic. That is also heat output. You can say. Okay. So heat input should be equal to heat output. First law is saying no. Energy can neither be created nor be destroyed. It should be conserved. So that will be applicable to find out the heat balance, right? Similarly, mass balance also people do. How much raw materials you are feeding, how much raw materials are accumulating in the reactor, and how much it is coming out. That also people used to do to find out, to know that how much coke is getting consumed or how much iron ore is going into the reactor to produce 1 ton of hot metal, for example. So my point is, finally I am concluding this. So why we do heat balance? Because we don't want to consume more amount of coke or more amount of fuel. If we consume more amount of coke and fuel, the cost of production will be very high, and that can be understood by heat balance. And it is related to first law of thermodynamics. Okay? Is it clear? Okay, fine. We will discuss this one, then we will end the class. Later we will discuss further. Second law. There are certain equations. I am not writing right now. I think you should understood first, then later we will write the mathematical equations and all. Again we will discuss, so that it will be easy for you. See, second law of thermodynamics actually related to this irreversibility. That's why I taught this irreversibility. So you will ask now why we study this reversible process or irreversible process. Actually, second law of thermodynamics is related to this irreversibility. What it's talk about? Acha, have you ever heard about entropy? Today we will not discuss entropy in details, but entropy, if you study thermodynamics, entropy will be coming every time. The same word will be repeated many times, entropy. Any idea you have? Entropy? What is entropy? Random, people call randomness. That is not true exactly. We will discuss that. But in simpler, people call randomness. If something becomes more random, that means more entropy. If something is ordered, it is having less entropy. People used to say like that, but not exactly, but we will discuss that. Anyway, so second law of thermodynamics is saying natural occurring processes are spontaneous, they are irreversible, and if you measure the change in entropy, it will be always positive. So how we represent entropy? S, mathematically, and change in entropy people use like delta. So this change in entropy is always positive. If a process is irreversible, spontaneous, entropy will always increase. That means, you can tell me today you measure the entropy of the universe, tomorrow you will measure the entropy of the universe. What will be different? It will increase or decrease or constant? Decrease. Increase. Entropy of the universe is continuously increasing. We are moving towards randomness, always. More randomness. You cannot do anything. But the concepts of this, listen carefully. Again I am saying, all natural occurring processes are spontaneous, they are irreversible, and entropy will be always positive. If you measure the change in entropy or total entropy, you can say, is always increasing. Or entropy of the universe is always positive. Or in other words, I can say, del S will be greater than 0. Total entropy, total, some people like total change in entropy is always positive or greater than 0. Maybe you cannot correlate what is entropy right now, we will discuss that. But if you talk to any mechanical guys, because they have also thermodynamics, maybe in this semester, I am not sure, you can talk to them. They have studied mechanical thermodynamics basically, but we study metallurgical point of view. So because they are dealing with engines, I told you, internal combustion engines and all. Piston is moving, so they are dealing with mechanical work, most of the mechanical work. Right? where heat and mechanical work are related. So so some people say like this, that heat will always flow from high temperature zone to low temperature zone, but it cannot flow from low temperature zone to high temperature. It is not possible. Fine. Suppose suppose this is one reactor and this is another reactor. This system. The temperature here is suppose 100 degrees centigrade, and temperature here is 25 degrees centigrade. So what will happen? If they are connected, you connect it now. You connect it. So what will happen? System always want to be in equilibrium, so there is a temperature gradient now. So that means these two are now not in equilibrium because there is a gradient in temperature difference. So heat will flow from this direction to this direction. But it will never happen that automatically the heat will transfer from here to here. Never happen, no? So you can say this is irreversible kind of thing, of course. So heat always flows in a particular direction. Energy always flows in a particular direction. But if you talk about a refrigerator, for example, fine. So what you need to do some work so that the refrigerator will get cool. Why? Because atmosphere is initially atmosphere inside the freeze, so it is not on condition, it is off. So temperature of the atmosphere and temperature inside the freeze are same initially, but the moment you on it, so you are doing some mechanical work actually, you are providing some external energy, that's why it is getting cooler with time, right? So that means if you want to send the heat from this direction to this direction, you have to do some work. You have to do some work, or you have to spend some energy to do this. But automatically this will flow. You do not have to do anything. Is it okay? You understand my point? Similarly, you take okay fine. Yeah, best example. You take a Coca-Cola bottle, for example, Coca-Cola bottle, okay? Or any thumbs up, your favorite cold drinks, anything. What is there inside? We have pressurized the carbon dioxide into that. So liquid is there, Coca-Cola, and carbon dioxide is in dissolved form in that. Because you have pressurized the CO2 is a gas phase. How it can stay in a liquid? You have pressurized it. The moment you open it, there is a sound and there is a hissing sound also. That means CO2 is coming out from there. So why this is happening? Because atmosphere pressure is 1 atm, but inside the Coca-Cola bottle the pressure is more than 1 atm. So automatically it will happen because there is a gradient in pressure now. You understand my point? But to provide CO2 into Coca-Cola bottle, you have to spend some energy. You have to do some work. Then only it is possible. So that is second law of thermodynamics saying. Second law of thermodynamics also saying that heat will flow from high temperature zone to always low temperature zone automatically. But if you want to reverse it, you have to do some work. You have to spend some energy. Mechanical people study like this kind of. But we people talk about entropy actually. Entropy always increases. Entropy will be always positive for a irreversible spontaneous process. In simple way. This is fine. That means randomness will be always increasing in the universe. Okay, let me talk about equilibrium finally and I will end the class. Here, let me give an example, the same example. If you take a Coca-Cola bottle, but inside the bottle what is happening, can you see? Macroscopically you cannot see, right? Even if you use something also you cannot see. But macroscopically what is happening? Some CO2 will be in the top part, like this for example. So this is a bottle for example. Up to this is liquid. This is a bottle. Up to this is liquid, Coca-Cola. But here some gas is there. That is nothing but CO2 actually. basically. And some CO2 is also here in dissolved form. That means inside the bottle there is equilibrium again. Equilibrium between what? Between this and this. That means the rate of forward radiation is equal to rate of backward radiation. That means the amount of CO2 going into the Coca-Cola liquid is equal to the amount of CO2 coming out from this and staying here. So that is also equilibrium. The rate of forward radiation is equal to rate of backward radiation. The amount of CO2 getting dissolved is equal to rate of CO2 coming out as a vapor and stay on the top part. But you can be able to see that. But macroscopically you can say nothing is happening. That is equilibrium now. Macroscopically you can say nothing, no change is happening. But microscopically it is happening and rate of forward is equal to rate of backward. So again this is called equilibrium. But if you open it, what will happen? Again it will start making an equilibrium between atmosphere and the bottle. Okay. Fine, we'll end the class here. I think you understood the concept.